Okay, good morning, everyone. I think nearly everybody's here. There are still a few of you who haven't yet submitted the data set to me. There's one or two who are in correspondence with me, but I don't think I've had a data set yet from a few of you. So this is showing you on the screen who I haven't yet had. So if you haven't yet at least started the conversation with me about your data set, you need to do that in the break today so that I'm sure that you are indeed on the right pathway, okay? So for all the ones I haven't yet agreed, we need to at least have a chat at the break. Okay, so this time I'm in my office, although I had a problem again. This time the university closed the west gate, so it took me a little bit longer. But I'm in the position now. Let me just shut my door just in case someone comes in. Okay, so I'm now in perfect peace and quiet, no construction outside my window. Okay, so last time we had got up to RO. So the ones that we looked at last time, we had looked at drug, which was an example of a general linear model because it had both a fact and a covariate. So in fact, the drug one is an example of the sort of data set I have in mind for the assignment. It has both one covariate and one factor. And we could look at the interaction between the two. That's, if you like a minimal data set for the assignment. The second one we looked at was the one about cars. And that one was challenging because, in fact, we had to rethink how the protection factor was written because it was written at the level of the car rather than the level of the driver or passenger. And we saw that when we simplified it so that we distinguished whether the position, right, the driver or passenger position was indeed protected by an airbag, then we got a very nice, simple model. We looked at the one about growth, which is a very simple data set, and it only had one X and one Y, but we saw that both a log transformation and a rank transformation, as long as we did log transformations on both X and Y, worked very well. And I explained that log transform both in that case was easily interpretable as an exponential growth curve. And then RO, the crucial point there was that one of the data points had very high leverage, meaning excluding that data point radically changes your conclusion about the model at best fit. And we saw from the 3D plot that in fact that reflected a problem with the experimental design in that nearly all the data points except one were almost perfectly in a plane. So that truly is a form of collinearity amongst the x's. So all the information in the third dimension came from just one data point. So it doesn't mean that data point is faulty, it just means it's very important. And ideally, we need some more data points in that direction so that we can be sure whether indeed that model is appropriate. So we're now going to look at the Longley data set. So the Longley data set is a very famous data set. It's particularly famous. Why is it particularly famous? It's particularly famous because it illustrates how poorly written statistical software can give problematic results. So, for example, What would be an example of that? So the early versions of Excel. So when Excel was first written, the statistical parts of Excel were very poorly written. So what do I mean by poorly written? Poorly written in the sense that just from numerical calculation perspective, they could give faulty or inaccurate results. So when I was taught as a grad student in statistics, we were expected to understand computing, which is quite common now in the context of data science, but we were also taught programming, including numerical analysis. So why does this matter? So on computers, these days, most calculations are done to what we call double precision. So that means that there are, I should remember this, something like the order of 20 bits of accuracy plus, I've forgotten how many bits are reserved for the exponent, right? But the key point is that the accuracy of double precision is quite high in the sense that rounding error becomes relative. The rounding error is going to be quite small, whereas single precision has much lower accuracy in terms of how many digits of accuracy we have. So when you're doing calculations, this can be a big problem. So just think about estimating the variance, for example. So if you want to estimate the variance, so let's say here we were looking at our values of y in Longley. We wanted to know what was the variance. Now you'll notice that the values of y are all in the range of 60 to 70,000. So if you try to calculate the variance by just simply saying the sum of the squared values minus n times the mean squared, right? Or sorry, the sum of the squared values over n minus the squared mean value, then you have a rounding error problem because the variability is down in probably the third or fourth decimal place at least, because the main thing that dominates the squared values of y is the mean, because the mean is quite large. So that means if you just try to calculate the variance by doing two sets of calculations, the sum of y and the sum of y squared, and putting that into the formula, mathematically that may be correct. But in terms of the accuracy of the calculation, where the precision is not perfect, which is what it is on a computer, you may get quite faulty answers, right? And in fact, if you look at the data set, there are even worse examples. So if you look at x2, well, there perhaps the variance is not that large compared to the mean, but x5, yes, x5 goes from what, 107,000 up to 130,000. So again, the average value of x5 is about 120,000. So you need to basically calculate the mean, then calculate the sum of the squared deviations around the mean in order to calculate the variance. If you try and do two separate calculations, you can get substantial rounding error in that calculation. And rounding error is in effect what happens, or indeed truncation error, depending on the computer when you do calculations and you only have a fixed number of digits of accuracy. So this particular data set, when it was put into the early versions of Excel, gave answers which were numerically faulty. It was giving actually the wrong answer. So that's obviously a big problem, right? Because then people actually reach the wrong conclusion and may not realize that they're reaching the wrong conclusions. So these days, of course, Excel has been fixed. The calculations are indeed good from a numerical analysis perspective, that they are careful not to have these problems. So this is when we go to the next level, which is doing regression type models. It turns out that what is a problem is not just if the mean is large compared to the standard deviation, but also if the scale of the different x's in our model is very different. And again, you will see x1, for example, is of the order of 100. x5 is the order of 100,000. So there's a scale difference of 100. So this, again, tends to make the numerical calculations much more tricky to get them to be correct when we're using finite precision. So, but actually, this is an interesting data set from a different perspective. So we can assume that JMP or Excel, when applied to this data set in these days, numerically gives trustworthy answers. However, as we're going to see, that doesn't mean to say that it doesn't have something useful to tell us. So what I want you to do first of all with this data set is to look at the fit of y by each of the x's. So we're going to put all the x's in here in the fit y by x. That means we want JMP to calculate all the separate simple linear regression models, right? So if we do this, so it gives us all the graphs. So I want you to do fit line for each of these 6 models. Okay. X1, X2, X3, X4, X5, and X6. Okay. So I want you to look at this and tell me in chat which of these variables you think are useful in a model for predicting y. Okay, so out of these 6 x's, you can look at the fitted models and the significance test for the slope of each of these and tell me which of these 6 variables you believe are useful in an overall model for y. Okay. Or p is less than 0.5. In fact, usually we don't use 0.5, we use 0.05, right? So typically people would test at 5%, not 50%, right? So which of these is significant? Yes, so except X4. So now, the reason I'm going through this example is because I repeatedly hear of statistics courses where the teacher says, before deciding what to put in your multiple linear regression model, you first do the simple linear regression model like this and would say, okay, I'm going to try including 1, 2, 3, 5, and 6. I won't bother with X4. And that's a very unwise process, right? What we can say is that we must at least include X1, 2, 3, 5, and 6. But we cannot know for sure whether X4 is useful because this just tells us whether X4 is useful on its own. It may be providing information that's distinct from the information from the other 5 variables. Okay, so what I want you now to do is to do fit model. Now we're going to put all of the x's into here together. Now, one more thing I wanted to I forgot to highlight back here. When we're looking at the separate x's, you'll notice that in all of them, there is a positive slope, right? So admittedly, X4, we're not sure whether it's significant, but at least the estimate of all of these is that the slope is positive. Okay, so now let's have a look at the overall fit. So the overall fit, so JMP sometimes doesn't do the summary of the fit, so please make sure you've turned on the summary of the fit. So the summary of the fit is that the adjusted R squared with all 6 of the x's in is 99.2%, right? So the best we got with the individual x's is, I think, 96% from X2, right? So it is pretty persuasive that there is a good linear model here somewhere. If you look at the residual plot, it looks pretty random. It doesn't look like there's an obvious problem with the residuals. If we look at the effect test, you'll see it indicates that x3, 4, and 6 are all very strongly significant. Now remember, this is a test saying, is each of these variables useful once we've included all the others? So this says at least x3, x4, and x6 are useful, right? x1, 2, and 5 do not appear to be useful, but this is just simply saying, given all the others. So it doesn't necessarily mean that we only need 3, 4, and 6. It could be that x1 is useful, for example, once we've taken out 2 and 5. Okay? So we know that we at least need x3, 4, and 6. It doesn't look like 1, 2, and 5 are useful. So you notice that 4, which is the one that on the individual simple linear regressions was least persuasive, turns out to be the most important, the most useful. Okay, so this in itself is interesting, but let's now look at the parameter estimates. You'll see that the parameter estimates show that of the 3 we are pretty certain we need, x6 does indeed have a positive coefficient, but 3 and 4 both have negative coefficients. So these two, which were not so persuasive, right, here with x3 and x4, actually turn out both to be very important. x6, you know, it's not surprising that x6 is useful, but it wasn't the one that was most significant at the beginning. Right, x2 is the one that was most significant on its own, and yet it's not clear that we need x2. Now, of course, we can do a comparison and see what happens if we drop some of these. So the effect summary in JMP tells us that actually x1 is probably the least useful of all these variables, right? So both x1 and x5 don't to be useful. We can remove x1. What happens? The adjusted R squared actually goes up a little bit. After removing x1, we can see that there's still not very strong evidence we need x2 and x5. So let's now remove x5. Again, it's not compelling, we need x2. We can remove x2. So this suggests that effectively we were just doing a simple backward stepwise regression there. So we should test this more thoroughly. But let's just have a comparison. If we compare the model with 3, 4, and 6, the adjusted R squared is about 99.1. We can ask it to show us AICC. So this is another way of comparing. Where's my AIC gone? Just a minute. Where's AICC disappeared to? I've lost it. I don't want the prediction profiler. I've lost it. Where is it put? Anyway, let me do side by side with this, the model with all of the x's in for comparison. So if we put these side by side, and we include the summary. So it's on the side here. Okay, sorry. So they've changed the report. So in fact, it's giving us AIC and BIC. So it says the AIC and the BIC in this simpler model. So AIC is about 242 against 255. The BIC is 240 compared to 241. So that suggests that using AIC or BIC, this much simpler model with just 3 variables is better than the 6-variable model, although the adjusted R squared has gone down a little bit. It's gone down from 99.2% to 99.1. And the residual plots look fairly similar. We can add in the plot the normal quantile plot to see whether that's a problem. Doesn't seem to be a problem in that one. We can add it in this one. Again, it doesn't seem to be a problem. It doesn't go that well along the diagonal, but it's well inside the confidence limits. Okay, now, so in this data set, I haven't told you what the Y's and the X's were and what's going on. So what we want to do then, first of all, before we find out what the Y's and the X's are, is to try and understand why our conclusions seem to change so much when we put all the X's in, or at least the three of them, compared to when we just put them in individually. So let's do a scatter plot matrix, and we're only going to look at the X's. Okay, we're going to ignore Y for the moment. Okay, so this is showing us the scatter plot of all the pairs of the X's. So what do you notice, right? What do you notice in this? Do you notice any strong patterns? Right, so please respond in chat. Do you see any strong patterns in the scatter plot matrix? What patterns can you see? Does there seem to be any strong relationships within the X's? Yes, 2, 5, 6 are correlated. Right? In fact, X1 to 5, 6, all of them are correlated. Right? X1 as well. Remember, X1 is only shown in this list. Okay? So 1, 2, 5, 6 are highly correlated. So now, so this is what's called collinearity. So again, I had a student who said to me recently, oh, if there's collinearity, then we should drop the X's. Again, absolutely not, because we don't know in the beginning what the effect of that collinearity is. So collinearity means that it's hard to distinguish between the information provided by each of these X's, in the sense that a lot of the information must be in common if the X's are correlated. But until we link it back to Y, we have no idea which of them is the one containing the most useful information, right? So the high collinearity tells us that when we fit the simple linear regression models, we probably will see fairly similar patterns when we predict against X, 1, 2, 5, and 6, which is indeed what we got. They all showed a fairly strong linear relationship. But which of them is the most useful one in terms of that common information, we cannot know without linking them back to Y, right? So, and in particular, putting them in together. So what we saw, we concluded in the end, was that X6 was the one that actually was most useful, it seemed. It seemed like once we included X6, that 1, 2, and 5 were not very useful. So let's just go back and look at the data again for a moment. If we look at the data, look at X6. Can you guess what X6 is? Right? What does it look like X6 might be? Yes, it's the year. So in fact, this is an econometric data set, which is basically asking the question, how did the US economy change across the 15 or 16 years after the Second World War? Right, so obviously after the Second World War, all that money and energy had been going in previously into building ships and aircraft and tanks to fight the Germans and the Japanese. Suddenly, all that energy could be turned back into economic output, useful economic output. So you would expect that in the post-war years, there would be a massive surge in the economy. So it's saying you first of all need to remove that effect. before you start to understand the other economic factors. So 1, 2, and 5, these economic measurements are also very strongly linked to the year. They also all increase with the year. So, and it appears that none of them tell us anything useful after we've accounted for the year. Whereas X3 and X4 are telling us something different about what's going on. So if we look at, so you will see the notes here don't actually tell us, it just says highly collinear regression data, right? But just knowing that the year is likely to be the underlying factor, we cannot conclude just by theoretical argument. We actually need to try and see what happens when we put 1, 2, 5, and 6 into the model together, which of them turns out to be useful, right? And then after we have removed the year effect, then we can see that what's left, X3 and X4, are actually telling us something quite distinct, which doesn't have much to do with the year. So X4 does generally increase with the year, and so does X3, but not entirely, right? They are clearly telling us something else about what determines the economic outcome. So, 2 key lessons. Don't try and filter out the X's based on simple linear regression. You may miss something important. And secondly, collinearity can be a problem in terms of accurately identifying which variable is important, and in some extreme cases, even in doing the calculations correctly. Or if you're using a competent statistical package, that shouldn't be a problem, right? However, we need to be cautious about reaching the conclusion about what is the best model. So in fact, we can go back in the fit model, and we can actually, okay, no, let me not go back here. Okay, so I think those are the key lessons. Now, there is one other slight issue. This Longley data set is actually a time series data set, right? They're in a time series sequence. So there is one more diagnostic that we should do in this case. So if you're looking at diagnostics, down the bottom here, we have Durbin-Watson test. So what's the Durbin-Watson test? It says a test that there is first order correlation. So in a situation where we have time series data, we shouldn't, potentially time series data, we should always check. This is saying autocorrelation means, is it actually true that the errors are independent across our data points? Is it possible that there is autocorrelation, meaning that the errors in years close together might be correlated, right? This is quite possible that would be the case in a time series set of data. If there is autocorrelation, then that actually means we need some adjustment to our conclusions because the errors are not independent. In fact, it's on the borderline. It says the autocorrelation is 0.13 and it's significant just at 5%. So autocorrelation of 0.13 is not a big deal. It means that successive errors have a correlation of about 0.13, but that means if I go 2 time points apart, the correlation is 0.13 squared. So we're talking about, maybe 2%. So there is a slight correlation perhaps between successive years, which is quite reasonable, and we might expect that. So we may have to be a little bit cautious that the true error of our estimates is maybe a bit bigger than we have calculated based on the assumption of independent errors. But as our significant levels for all of our 3 variables is significant at less than 0.1%, or sorry, less than 0.12%, it's not likely that adjusting for autocorrelation is going to make much difference, right? It's fairly clear that as the year goes up, this economic outcome is going up, but X3 and X4 both have negative coefficients, okay? So again, some important lessons for us in general about that what people assume to be correct. It's also interesting to me in the sense that it tells us that AIC and BIC in this case reach the same conclusion, that the simpler model is better. Adjusted R squared, however, it still chose the more complex model, right? In fact, if I remember correctly, it thinks we should still include x2 if you use adjusted R squared. So adjusted R squared probably does tend to select models which are a little bit too complex. But at least when we compare with the, I should have compared this again to the one with all of the variables. Oh, sorry, this is the one. Yeah, so although the one with all variables looks better, there are still ones which even adjusted R squared thinks are better than putting them all in. If I put all of them back in, but now remove x1 and remove x5. If you look at this one, you can see the adjusted R squared is clearly that higher than the one with all 6. So at the very least, it suggests we need to drop x1 and x5. It's just an issue about whether we also need to drop x2. So you'll notice that is significant at about 3% in this model, right? But AIC and BIC, let me put these back in here. AIC and B, so yeah, AIC and BIC still prefer this model with x2 in as well, right? Right, so the only real question, if you like, is whether we need x2 as well. Okay, so let's look at another data set. Let's look at Linear-Rand. So Linear-Rand is another one which is going to give us guidance about model choice. Where's my full? Here we go. Jump too fast. So Linear-Rand has a large number of x variables, and our outcome variable is oxygen uptake, right? So this is meant to be information predicting how much oxygen people take up. So we're going to try and fit a model. So we're going to start trying to fit a model for all 30 of the x's. Clearly, this is far too complicated. So I want to use this example to illustrate the problems of trying to do model selection without being careful. So I want to choose stepwise here. Now, so we're choosing y2 as the oxygen uptake, all of the x's. Now, within the stepwise, I want to start out. By looking not at BIC or AIC. We're going to use p-value threshold. Okay. Now, your p-value threshold may be set to different default values to mine. So these are the standard defaults in JMP. And you'll see it's set 25% to enter and 10% to leave. Okay. So the idea being we're doing an initial screen through all of this. We want to make sure we haven't missed anything that might be useful. Okay. And then the direction, we can do forward, backward, or mixed. So it's quite clear that mixed is generally a better approach. It's more likely to find the best model. So we'll choose mixed. That means after adding each variable, it will see whether it should drop one. Okay, so it will do successively add and drop until it can't find anything to add or drop. Okay. So if we say, please go off and find a model, you will see that it's actually found a model with 13 variables, 13 out of our 30. In fact, you may get a slightly different answer because you may not have quite the same data set as me, but at least we have quite a large number of x's in our model. Okay. So now we can choose make model. Make model means it takes us back to the standard regression model. And then we can say run. And so we end up with this model that says, again, if we look at the summary of the fit, I get a summary of a fit which has 66% as the adjusted R squared. If you look at the effect test, that looks a little bit worrying because X3, X4, and X29 in mine are all not significant individually. But you can see I've got at least two variables which are significant at 0.01%. That maybe if I chose the cutoff at 0.1%, you can see there's quite a large number of variables which are significant. Okay, so what's the conclusion from this? The conclusion is apparently I can find a useful model based on this overall assessment. So what's the problem? Well, the problem is, if you now go back and look at the data set, so click on X1, go to columns and formula. If you look at X1 columns formula, you'll see the formula says random uniform min-max. Min-max means it will be random uniform 0, 1 by default. It's using that default. In other words, all of our X variables in here are pure randomly generated noise on a uniform distribution. There is absolutely no relationship between the X's and the Y. So what's going on here? Well, it's because we're doing multiple tests. So if you think about it, let's go back to where we started out. So when we started out here, the first step of the stepwise regression was it effectively looked at the 30 different X's and said, which of these is most significant? Is it significant at 25%? Well, even if there is no relationship, these 30 significance levels should then be random uniform from 0 to 1. So the smallest, the 30 random uniform 0 to 1, I would expect to be about 3%, let alone 25%. So just by chance, I probably included the first X. In fact, if we go back to the beginning, if we say remove all, we can now try, you might say, well, those p-values were ridiculous. Let's change them to 5%. Okay, so if we change them both to 5% and say go off and do it, it only adds in one variable. Right, so that's not quite so bad, but even then it's a little bit worrying. Why would we get one? Well, again, as I said, we're doing 30 tests. So in the course book, I talk about using Bonferroni correction. The Bonferroni correction says, in simple terms, that we need to multiply the significance by the number of tests to get the true significance level. So 5% times 30 is 150%. So that's not a meaningful cutoff. So at the very least, I should reduce this down to something much closer. So in fact, if I change this to 1%, for example, you'll see I get nothing, right? So indeed, because the smaller significance level I have here in that initial test is about 2%, right? So as long as I choose a small enough significance level, I don't get silly answers. All right, so the temptation is to say, well, the ends justify the means, because even though I originally set the p-value at, say, 25%, I've got all of these p-values here, variables put together, which are highly significant. But that's not trustworthy, because actually I'm doing so many tests. If you think about it, if I've added in this number of variables, 13 variables, that means I've done 13 different tests. And in each of these, actually, there's close to 30 tests being done. So I have done hundreds of tests. So it's not surprising that I get many tests which appear to be significant at 1% or less. Okay? So we need to be careful. So even AIC and BIC have a problem in this particular example. Now, this is a very extreme example. Why is it extreme? Because if we go back and look at the data set, you will notice we have 30 X's and we have 31 data points. So in fact, if we try to fit the whole model, if we try to fit the model, how does the auction uptake depend on all of these X's? It can't give us any effect tests. Why? Because there are no degrees of freedom left in our effect summary, right? So if we look at the summary of the fit, it tells us, yes, R squared is 1, adjusted R squared can't be calculated, right? Because we've got one parameter for every data point. So just like fitting a straight line through 2 points, if we have 30 X's, we can fit perfectly to 31 data points, right? So clearly then, it is not a very sensible data set to start looking for all of the X's when our number of X's is just as big as our number of data points. So you'll see people will suggest things such as a number of parameters should not exceed the square root of the number of data points. So there is no clear rule, but we need to be much more cautious in interpreting the results if the number of parameters is large compared to the number of data points. It's quite possible that we will get models which are overfit, right? We're overestimating how good those models are because we don't have a lot of information left over to test how good that model is once we've put in a few variables, okay? So the key lesson from here then is A, be very careful when the number of variables is large. B, be very careful with the default significance levels in any form of stepwise regression, particularly because you need to adjust those significance levels. But in fact, I meant to show you. So even if we had not used p-values, what I didn't actually show you the outcome if we used AIC or BIC. The problem doesn't entirely go away. So if we had said minimum BIC, now we can't, well, we can tell it to try and do mixed. See whether it actually does it. No, it will not allow us to do that. So we have to do forwards. So let me just do it again. So you will see minimum BIC doesn't lead to a sensible answer. Right? It keeps thinking that BIC is improving. Similarly, if we use minimum AIC, we still end up with a model which has, I think, 6 variables. So in these more extreme situations where the number of parameters are large compared to the number of data points, we may still get answers which are not sensible. We need to be careful. And in fact, AIC and BIC implicitly assume that the number of parameters is relatively small compared to the number of data points. Otherwise, they also break down. Okay. So now we're going to look at 2 examples where quite a lot of the variables should be useful. So I want you to look at the one called body measurements. That one I've already adjusted. Let me go back to the original one. Okay, so the body measurements. So what we have here is a large number of measurements on the body of, I think, 22 different individuals, okay? So these 22 different individuals, we have their mass, or if you prefer, their weight, and then we have forearm and bicep. So forearm means the lower arm, bicep is the upper arm. We have the chest, we have the neck, we have the shoulder, we have the waist, the height, and then we have the calf and the thigh, which are upper and lower, lower and upper leg, and we have the head. So, in other words, we have all these different measurements of the body, which in principle should be related to someone's weight, right? So obviously you would expect the height. So height clearly relates to the bone development in the body, right? So the height is primarily about bones. Similarly, the head is about the skull, right? So skull we wouldn't expect to be particularly useful because skull sizes don't vary very much usually. They don't normally vary with the height. The waist. So the waist we would expect to be the best indicator maybe of body fat. And then the forearm, bicep, best indicators of muscle in the arms. Calf and thigh, perhaps the muscles in the legs. The chest, perhaps the muscles in the chest. Neck, maybe not too obvious what the neck would have. You might think that it's not going to be particularly good as a predictor. Shoulder, again, shoulder you might think is primarily the bone, but maybe it's also the muscle around the shoulder. So we can see that some of these relate more to the bone structure of the body, some more to the fat, some more to the muscle. So in this situation, we would expect that if you have all these body measurements, it should be able to predict the mass fairly well, but it's not going to be obvious what is a good, relatively simple prediction for the mass, okay? So we might just start saying, well, let's just try fitting a model. Let's try and predict the mass given all of these other measurements. So if we try putting them all in together, if we look at the summary of fit, it says that the adjusted R squared is of over 95%. So clearly we can predict the mass fairly well. The challenge, though, is to find a relatively simple model. So if we look at this, you'll see that actually only 2 of these dimensions are clearly quite strongly significant after adjusting for all the others. So not surprisingly, the single best predictor is the waist, and the second best predictor seems to be the height. So, for example, let's just think about it. I assume most of you have heard of BMI, right? So what is BMI? So BMI is a very crude way of indicating whether somebody has a healthy body or not. The logic is that the body mass index is the weight divided by the square of the height, right? So you think about it, the weight divided by the square of the height. So that's a rather odd sort of measure on the face of it. So if you think about it, your height is something you can't control, right? It has nothing to do with your diet or anything else or your exercise. Whereas your weight, clearly you can control to some extent through exercise and diet, and maybe your health, right? So clearly your weight will increase with height, So implicitly, this is based on the assumption that the body weight increases with the square of the height, and the bit that's left over is the bit which is telling us whether you're relatively fit or unfit, right? So implicitly, we would expect definitely to include the height in any prediction of the body mass. Waist also we would expect to be a good predictor, simply because it's probably the single best predictor of somebody's fat, body fat. Now, the fact that all of the others are not significant doesn't mean they're not useful. It just means, given all the other variables, they don't appear to be useful. So we probably can find a simpler model than this. So again, if we look at the effect summary, it says the shoulder is the least useful. Well, that's not surprising. It's not at all clear how the shoulder relates to weight. The bicep is not particularly useful. That's a little surprising, right? But maybe it's because there are other better measurements of the muscle. The neck is not particularly useful. Again, not too surprising. The chest, so again, maybe the muscle on the chest is better indicated with other variables. The calf, so again, maybe the thigh is better, telling us about the leg. The head is not very useful, not too surprising, because the height is, well, the head doesn't vary very much. So then we end up with these four variables: waist, forearm, height, and thigh. So effectively, you can think of it as the waist telling us something about the fat. The forearm and the thigh are essentially talking about the muscle in the arms and legs, and the height is the bone, right? Now, that on itself is not too bad. The adjusted R-squared of this model is about 96%, right? We can try doing a stepwise regression. So for example, if I put all of these in here, I say do a stepwise, and I'm going to say, well, I'll perhaps choose BIC, say go and find me the best model under BIC. And the best model under BIC is very similar to the one I've got here. It just includes head, right? And in fact, the head is the least useful of these five. If we change it to being AIC, we get exactly the same model as I have on the left: forearm, thigh, waist, and height. Right? So seems like, 4 or 5 of these variables are useful and gives a reasonable prediction. And so some people might just stop there and say, okay, I have a reasonable linear model. What's the problem? Well, the problem is how to interpret this. So if we look at the parameter estimates here, indeed, the parameter estimates are all positive. So that's somewhat reassuring, right? We would expect that our estimate of the weight would increase as each of these increase. But how do we interpret this model? What is the scientific interpretation? So it's a bit problematic. So again, if we want to think about it a little bit more, I said the BMI, we scale the weight by the square of the height. So is that reasonable? So if we think about the human body, we can think about it, the size of your body is essentially the volume of an object, right? So the volume of an object is length times width times height. And we have a constant of proportionality that depends on the shape of that object. So for example, a cylinder, we've got one coefficient of, if you like, area times height. A pyramid has a different coefficient of base area times height. But essentially, these are, for most objects, it's essentially some sort of an average area times height, right? So if you think about it like that, then we should be expecting that mass is roughly proportional to waist times height times maybe something else, some other measurement, right? So we would expect that. So if that's the case, it suggests that maybe we should be looking at something on a different scale, right? Maybe we should be looking on a log scale, because like we said before, a multiplicative model becomes an additive model after a log transform. So let me try something different. So let's try doing a log transform of all of our variables. Okay, so I'm going to create new columns. I want these all to be, and I'm going to use log 10 because I can then easily, sorry, let me not do it that way. Just do columns, new columns, log, and I want to put 10 of these at the end. I apply this, and now I'm going to do each of these. I'm going to say column info. So the first one I want is log of mass. So my formula is very simple. It's mass and then transcendental log 10. Now I can sort of cheat. I can copy and paste this one into the others. So the second one is, log forearm, formula, edit formula. I'm going to paste that value in and just change mass to forearm. It's my second one. My third one is bicep. And replace mass with bicep. And you'll see it's showing me the formula in the screen so I can see that I've got it correct. So log mass, log forearm, log bicep, log chest. I'm pasting my values in again. I need to keep remembering to change the thing I'm doing the log transform over. Again, fortunately, it warns me, shows me what I've done. Log of neck. Log of neck, log of shoulder. That's right. Waist. Waist. Height. Let me change all the names first so I make sure I get them right. Calf. Did I miss one out? What have I done wrong? Oh, I said 10 instead of 11, right? I missed one out. Should have done 11. Log of calf. And thigh, so I've missed that head. I need to do one more at the end. This one should be height. Calf. And thigh. Oh, it's difficult to see on my screen. Oh dear. Oh. Right, so I'm missing my last one. I need to add in one more. I forgot it's actually 11 variables, including the dependent one. So I want log of head. Okay, so once I've done all that, I now have my new 11 variables. So we can compare the model we get if we do it on the log scale. So, as I've mentioned, so I said, if this is basically an argument about volume, then of course volume times density is equal to mass, right? So we've got a log of density part which is not actually constant. So the point is that the density varies across these different measurements, things they're linked to, whether they're linked to the bone. So the bone is where the density is highest, followed by muscle, followed by fat, right? And we've got internal organs, I guess, which we don't really have a measure of. So let's have a look at this. So this is with all of our variables in. So clearly we don't need them all. And on the log scale, it's suggesting we can drop neck, we can drop bicep, we can drop chest, we can drop shoulder, we can drop calf. So we're back to essentially the same 4 variables, but how well does this one fit compared to the one on the non-log scale? Well, actually, it fits a little bit better, not a great deal better. So what's the advantage of this one? The advantage is I can look at the parameter estimates and interpret these. So this is telling me that the coefficients of log forearm, waist, height, and thigh are all between 0 and 1. Right? So if I think about it, implicitly, if I only had 3 of these, I would expect the coefficients to add up to about 3, right? On the log scale, the volume depends on the cube of the linear distance, right? So after taking logs, I should expect that the sum of the coefficients is about 3. So if I really had measured length, width, and height, I would expect the coefficients all to be 1. As I have 4 measurements of the linear distance, they should roughly add up to 3. And in fact, that's not too far off. Here, I think they add up to about 2.5 or 2.6. So I can interpret this as approximately like that. In fact, if I simplify it down, I could, for example, let's see what happens if I remove one more. So if we remove we remove down to 3 variables, you will see that the coefficients of forearm, log, waist, and log height are all not too far from 1. So log forearm is 1.02, log of waist is 0.8, but with a standard error of 0.13. Log of height is 0.7, but with a standard error of about 0.23. So in other words, it suggests that a not too bad model might be that mass is proportional to forearm times waist times height. So indeed, I can even try and create a new column. Simple predictor. And I'll put in my formula, log of forearm plus log of waist plus log of height. Let's see how well this does. Oops, I got one too many pluses. Let's see how well this predictor works. So my simple predictor here. How well does that do in predicting log of mass? You can see it's not too bad. We have an adjusted R squared, which is actually not too far off, right? The one we had just now with forearm, waist, and height we've gone down a little bit. So we started out with about 0.95, I think. So we're still an adjusted R-squared of about 95%. Right? So this is a relatively simple explanation. This says that the mass is, log of mass is essentially proportional to forearm times height times waist. Right? Now we can clearly do better than this, but at least that's a reasonable, simple model, which fits almost as good as any other model we can find for predicting the mass. Right? We could be a bit more sophisticated. We could average the forearm and the thigh, for example. We could choose, I could have done that, so we could choose a slightly more complex predictor based on that. But this at least is a very simple predictor. Essentially, it's just the only parameter left now is effectively the coefficient of my simple predictor, which is 0.87, right, rather than 1. Okay, so we can come up with relatively simple models. The advantage of the log transform is that we can interpret this in a relatively simple way. It says that the mass increases proportional to the waist, proportional to the height, and proportional to the forearm, right? Which is very easy to interpret and is almost as good as the best predictor that we can come up with. Okay. So I can't say that. Yeah. Okay, so let's have a look. What else can we do? So the last one that we're going to look at in this particular set is the decathlon. So this is, so does anybody know what the decathlon is? Anybody in chat? What is the decathlon? Yeah, it's a store. Thank you for the little joke. But the reason it's the name of a store is because it is possibly the most prestigious Olympic event. Right? Why? Because it's the Olympic event where you have to be the best all-round athlete. Right? So you will see it has the 100 meters, the long jump, the shot put, the high jump, the 400 meters, the 100-meter hurdles, the discus, the pole vault, the javelin, and the 1500 meters. So you have to be able to run sprint, you have to be able to run longish distance, you have to be able to jump over the hurdles, you have to be able to throw the discus and the javelin, you have to be able to do the high jump, long jump, and the pole vault, which is essentially something like a combination of long jump and high jump. Okay, so you need to have muscles all over your body. Now, I should point out a slight problem with this data set. You'll notice that we have names. So actually, for people like Dan O'Brien and Daley Thompson and Jürgen Hinson, they're in here many times. So these are not truly independent observations, right? We're ignoring, for the moment, these are the same individuals measured on multiple occasions. If I remember correctly, this is basically their performance in elite competitions, okay? But for the moment, we're going to ignore that. The key question is, how do these different things link together? We could just try and predict the score, but what I did, I thought that's a little bit boring. Clearly, the score depends on how well you perform in all of these different events, right? And no individual can be the best in all events. They clearly have to balance off their abilities. So what I've proposed here is to try and predict 2 events from the other events. So that's not quite so obvious, right? So if I want to predict 100 meters, for example, so which of these other events do we think would best predict the 100 meters, right? So anybody want to suggest which 2 or 3 variables would best predict the 100 meters? Given you've got long jump, shot put, high jump, 400 meters, 100 meters hurdle, discus, pole vault, and javelin. Hurdles and long jump. Anyone else? Yeah, so those are not bad guesses. The 100-meter hurdles is again a short distance run, although it also involves you have to jump over the hurdles and you have to have the timing. The long jump isn't a bad guess either, because in the long jump, you basically have to sprint down the runway before jumping. And in fact, Carl Lewis famously, is Carl Lewis? I don't think Carl Lewis is in this particular set. So Carl Lewis was an Olympic medalist in, I think he wasn't in the 100 meters alone. If I remember correctly, was it the 100 meters relay or something? I can't remember. Anyway, so that clearly there are people who are very high performers in both long jump and 100 meters. But you might think about the other races. So 400 meters actually does require fairly fast running, right? But you wouldn't expect things like the shot put and the discus, for example, to be related, because those are basically upper body strength. 1500 meters, so that's an interesting one. So these are running events, but it's basically a relatively long distance, right? So it's more about your stamina than your ability. So let's have a look. So we can actually start this just to see how well it does. So predicting the 100 meters from all the others. And perhaps we'll try the stepwise just to start with. So we'll try the BIC and see what it comes up with. So the BIC indeed comes up with 4. It has long jump, 100 meters hurdles, 400 meters, and 1500 meters. However, look carefully at the model. We need to look at the parameters, and you'll notice that actually 2 of them are negative. However, we have to be careful in 2 ways here. First of all, if you think about it, not all of the events are measured in the same way, right? So the running events are measured in time. So lower is better. Whereas the jumping events and the throwing events are measured in distance. So bigger is better. Okay? So this is telling us the better you are at long jump, the better you are at 400 meters, and the better you are at 100 meters hurdle, the better you will be at 100 meters. However, the coefficient for 1500 meters is negative. So that says actually people who are good at 1500 meters are likely to be less good at the 100 meters. Okay, because they're both measured in time. So in other words, you basically have to decide whether you're going to choose to put your effort into short distance running or long distance running. Okay, now again, this is not a random sample. Remember, this is amongst elite performers. So if you don't already perform pretty well in all of these events, you're not even going to get into an elite event or even try, right? So if somebody like with my body shape is clearly never likely to be good at short distance running. So in fact, if you're not good at short distance running, you might have a struggle with 100 meters. However, it's an interesting issue about body shape. So if you look at Carl Lewis is quite tall. So for long jump and high jump, elite performers are generally quite tall. That's generally not true for 100 meters, right? So sprinters tend to be relatively short, but not so much necessarily, right? So somebody like, who's our previous Olympic guy, right? Yeah, Usain Bolt is not that short. So things change over time in terms of what people assume is the right body shape for an event. But generally, long distance and long jump and high jump, people are taller. Sprint less so, right? Because it's more about your legs, the muscles in your leg rather than the length of your legs. Okay, so that's interesting. Again, we could arguably do log transforms here as well, because again, these are likely to be multiplicative in scale. right? We could, but I'm not going to spend time on it here. I just wanted to use this because I think it's an interesting illustration that our intuition isn't always that great in a situation like this. In fact, this model isn't too bad. It's explaining more than half of the variability, right? And you can see all 4 of these variables are strongly significant. Okay, what about the other one I was proposing was, oh yeah, pole vault. So pole vault is again a tricky one because generally that's one where it's not so easy to think about what would predict pole vault. Anybody want to think about what might predict pole vault? Right, so pole vault could be seen as, yeah, so it's a little bit like the high jump, except you've got a stick, right? You're basically saying, how high can I go? But rather than just jumping over, you have a stick to help you get over. In fact, the high jump went through a radical change, I think around the end of the 20th century. So somebody called Dick Fosbury came up with the Fosbury flop, right? So before Dick Fosbury, people doing the high jump tended to sort of just run down the runway and then just jump, trying to put their legs over the bar. And Fosbury realized that you could essentially do a backwards flip over the bar, and hence he was able to jump much higher than anybody else. So he basically changed the standard technique for high jump radically. Yeah, so high jump, yes. So shot put, yeah, so shot put is about upper body strength. So it sort of depends on how important you think the upper body strength is going to be for pole vaults. So let's have a look and see. So again, let's do stepwise just to give us a quick idea. See what shows. So this tells us, okay, so again, we have to be a little bit careful because of this issue of switching between distance and time. So pole vault, long jump, shot put, javelin are all distance, right? 100-meter hurdles and 1,500 meters are length. So interestingly, this is telling you long jump, high jump, shot put are all negative, and javelin, right? So this seems to suggest that pole vault doesn't have much to do with the other events, right? It's something like saying if you're good at long jump, you're not particularly good at pole vault, right? So it's a different type of upper body strength from long jump, shot put, high jump, and javelin. And then the 100-meter hurdles is positive, but that's a time event. So it's saying it's the reverse, right? So in fact, all of these events seem to be telling us the reverse direction, right? So pole vault, you would expect long jump, shot put, high jump, and javelin to be positive, and they're all negative. And then the distance events, you might expect them to be negative because they're in the reverse direction, and those are both positive. So this is basically telling us that people who've optimized their performance in the other directions tend not to be the ones who are good at pole vault. So again, this is basically warning you that this is about selection amongst the elite, right? So amongst people who are already very good athletes, this seems to be telling us people who specialize in pole vault are the ones who are not particularly good at the other events, right? So it's basically a way to get points if you're not a first-class athlete at one of the others. Okay, so it's a very odd one until you realize that this is selection within the group. Okay, I think that's a good time to take a break. It's now 11 o'clock, so anybody who has not yet had the conversation with me about the data sets by email, now is your opportunity. You can chat with me by private So that means, I think Jackson sent me an email, but we hadn't reached a conclusion. Mac Yutong sent me an email, we hadn't reached a conclusion. Chi Chun and Nicholas had sent me an email, we hadn't reached a conclusion. Okay, so we don't have to reach a conclusion right now. So for those of you who have already started the discussion, that's okay. But I think Chi Chun, yeah, maybe Chi Chun is the only one who hasn't sent me anything at all yet. Okay, so maybe you can send me a quick message, at least to tell me when I can expect to receive something. Okay, and so we'll start again at 11:15. Okay, so I am going to stop the video. Okay, so we had looked at Longley, Linerand, body measurements, and decathlon. So we're now going to look at three very different data sets that illustrate more sophisticated analysis that we might sometimes need to do. Okay, so the first one I wanted to look at is the one called animals. Okay, so the animals one is more sophisticated in at least two important ways. First of all, you'll notice that we've basically got two species of animal, right? We've got two species of animal. We've got foxes and coyotes. And within those two species of animals, we have got three subjects. So first of all, the subject number then, this is a random animal from that species. So that random animal from that species is what we call nested within the species, because subject one, so fox one, has nothing to do with coyote one, right? Those are completely different things being looked at. So we need to recognize that the subject is nested within the species. Okay, that's the first thing that we need to consider. The second thing is we have repeated measurements. So we have, for example, for the fox subject one, you will see we have four measurements. We have the measurements taken in fall, winter, spring, and summer. So in other words, we have four seasonal measurements. So this is basically how far does the animal travel in different seasons. Okay, that particular animal. So these are repeated measurements. In other words, the subject not only is nested inside species, it's a random effect, right? So we have these repeated measurements. So that means the standard linear model assumptions are faulty because the variability within subject, right, is what we're focusing on here. So each measurement has both a subject effect and a measurement effect, right? So the errors on the first four measurements have to do with both the subject variability and measurement variability. So within JMP, we have to be a bit more careful about fitting our model. So we're going to choose fit model. So the easy part is we're trying to model the distance traveled, right? So the distance is in miles. In fact, there is a slight problem with the distance measure here. You'll notice they've all been rounded or truncated. So we don't actually know which it is. They've either been rounded or truncated to an integer, which is a bit odd. What we really want to know then is how the distance depends on the species, how it depends on the season. We could even involve an interaction between those, but we know it also will depend on the subject. But the subject is nested. So if we look at attributes, this is a random effect, right? Subject is a random effect, and also subject is nested within species. So we need to select subject as being nested inside species, and we need to say that it's a random effect. Okay, so this is, as I said, it's different in both ways. Now you'll notice that JMP has changed the analysis up in the right-hand side. So it still says standard least squares, but the method, you will see it says REML and EMS. So what does this mean? REML is the recommended method. This is restricted maximum likelihood. So this means it restricted in the sense it recognizes that the two variance components, variance cannot be negative, right? We can even tell it we only want to estimate the variance components if we were only interested in the random effects. But here we want to understand both the fixed effects, species and season, and we want to take into account the subject effect, which is a random effect. So if you think about it, in the F-tests here, they have to be adjusted because we need to account for both the subject variability as a random effect and the measurement error on each observation. Okay? So if we now run this model, you will see that it treats the subject effect separately from how it treats species and season. Okay? So it's showing us in the parameter estimates only the species and season effects. The subject effect is showing as a variance component. So it's saying of the variability in our data, how much is due to the subject, how much is due to the residual. So residual meaning the individual measurements on that subject. So it's saying about 1/3 of the variability is due to the subject effects, and about 2/3 is due to the measurement effects. So it needs to take account of this when it does the F-test. So you'll see it's done an iterative approach. It has to repeatedly estimate because it has to estimate both the variance effect and then based on that, estimate the parameter estimates, and it iterates back and forth on these until it reaches convergence. So you will see it shows us overall the season effect is very strong. So seasonal effect is significant at 0.05. So there's no question there is a strong seasonal effect. The species effect is sort of borderline. It's not very strong. It's significant at about 3%. And if you look at this carefully, you will see why it's a little bit odd. So you'll notice, okay, degrees of freedom, that's easy, right? There's two species, so there's going to be 1 degree of freedom in comparing species. 4 seasons, so 3 parameters, 3 degrees of freedom. But look at the degrees of freedom of the denominator, and you will see species is only 4 and season is 15. So why is that going to be the case? Because for the season, we can basically use all of the data, right? It's all telling us about the seasonal variation. But for the species, right, we've first of all got to estimate the species effect after accounting for the subject effect. So it's adjusting, changing the F-test for the species effect to account for the fact that we've got these subjects within the species, and the subjects themselves are a random effect. Okay? So this is telling us a more sophisticated analysis, and it's enabling us to still test whether there are season and species effects, but accounting for the fact that because we have a random subject effect, that needs to be accounted for in the F-test. And we've also told it that the subject effect is nested within species, so it recognizes that subject 1 inside fox is a different subject to subject 1 inside the coyote. Okay? So this means we can account for both the random effect and we can account for nesting, and we need to recognize that we're adjusting. So in the workshop I ran for the grad school on hierarchical linear models this week, I don't think any of you were in it. I'm not sure. If you were, I discussed a Bayesian approach to hierarchical models like this, which is arguably superior because it fully accounts for the hierarchical nature of most random effects models. So actually, if I really was analyzing a data set like this, I would normally analyze it as a Bayesian hierarchical model to fully model the random effects. Okay, so that one is not that complicated once we have realized that we cannot use. So the real lesson for here is you need to be very careful when you've got repeated measurements on the same individuals. You should be accounting for that with a random effect model. Okay, now we're going to look at something quite different. Up to now, we have been focusing entirely on linear models with normally distributed errors. What we're going to now do is look at binary and ordinal data. So this is the Spring data set. In fact, I see there's two versions of this. Yeah, it's the one called Spring, not the one called Spring Data. So Spring. So the data set called Spring. So this is a rather small meteorological data set. In fact, it's not a very sensible data set because it's got lots of redundant information in here. We've got the month in here in three different ways: as a number, as text, and as part of the date. And then we've got the day of the month twice, once as part of the date and once separately, none of which we're going to use. So what we're interested in primarily is we've got the temperature, we've got the air pressure, we've got the humidity at 2 times of day, we've got precipitation. So what's precipitation? That generally means rainfall, but precipitation is more general than rainfall because it also includes any hail or snow. So if you get hail or snow, you basically melt the hail or snow and measure the equivalent rainfall. We then have the wind direction and the wind speed. So for some reason, I've done the wind direction at 2 time points and the wind speed only at 1. And then lastly, we've got this variable called sky cover. So sky cover is an ordinal variable. So this is, I believe, a relatively subjective scale assessing how much of the sky is covered with clouds. So 0 means absolutely clear sky. 10 means the clouds completely cover the sky. So obviously you won't normally have rainfall without some form of cloud. So all the ones with precipitation indeed have at least some sky cover, but not necessarily a high degree of cloud cover. And similarly, cloud cover does not guarantee precipitation. So what we're going to do is create one new column first so that we can look at this as a binary outcome. So our binary outcome is going to be whether it has rained or not. So I'm going to call this rained question mark. And this is going to be a nominal scale variable. We could choose ordinal as well. In fact, it doesn't really matter because it will be binary. So it doesn't matter whether we choose ordinal or nominal. So what's my formula? My formula is going to be an if-then statement. So if something, then something. So if it rained, so that means the precipitation, and then I do a comparison. So if the precipitation is greater than 0, so I type 0 into here. So if the precipitation is greater than 0, then I'm going to put in double quotes, rained. Else, dry. Okay, so if I've done it correctly, let's see if I've done it correctly. Indeed, we can check, we can do a table, fit y by x, where we look at the precipitation against rained, and we should indeed see. We can look at them. Actually, I want means and standard deviations, not means and analysis of variance. So the means and standard deviation, so if it's dry, then indeed the mean and standard deviation are both 0. That means because it never rains, there's no precipitation. Rained, although there may be a very tiny amount of precipitation, it is not 0. Okay? So what are we going to do now? So the question then is, can we predict whether it rained or not? So what might we predict it with? So we might say, well, let's try and predict rain using the temperature and the pressure and the wind speed, right? These might be all possible variables. Now, the wind direction, as it is in here, we can't use it directly. Can anybody think about why we can't use the wind direction as it is written here? Right? What problem is there with using wind direction as a variable in a model? Anybody think? Yeah, because it basically flips around at 360. So 360 and 0 are the same in a wind direction. So we can do this by essentially converting it into north-south component and an east-west component. Right? So direction can be very useful, but we need to be careful that we have not just used the wind direction directly. We would need to account for the fact that it's basically a 360-degree scale. So in fact, or a 2 pi scale if it was written in radians. But I mean, this is, I suspect, in degrees, oh, it's not clear. So in fact, wind direction is very important. So if you consider Hong Kong, for example, if the wind direction is from the south, then the wind is bringing us wet air from the sea. If it's from the north, it's generally bringing us dry area from the mainland. Right? So the wind direction actually is quite important. We should really use it. I don't know how important it is in this particular data set, but let's just try and look at this. Now you'll notice JMP has automatically changed the personality to nominal logistic, meaning it already recognizes that we have a binary outcome. So it's fitting a nominal model. So it's automatically done this. Now there is another choice here. We can choose generalized linear model because generalized linear model includes logistic. So if we chose generalized linear model, we would then have to tell it this is binomial data. And so binomial and a logit link function is the same as fitting a logistic model. But we actually have another choice in here at least, which is probit. So logit and probit are different ways of converting probabilities of an outcome back to a linear scale. So logit means log probability over 1 minus probability. So if probability is the probability of, say, rained, then 1 minus probability is the probability of dry. So we're looking at the log ratio of the probabilities of rained and dry. That's a logit model. A probit, instead of using a log function, probit means use an inverse cumulative distribution for a normal distribution. So in other words, probit is essentially saying our variables are predicting a probability where that probability, it comes from a normal distribution rather than a logistic distribution. So generally, logit is much easier to interpret, and the results are usually fairly similar. So we can just choose nominal logistic. Now you'll notice it says target level, we can choose. Now, as we can choose what is our primary outcome, dry or rained. Well, in our case, it's rained. We want to know what predicts whether it rained, right, relative to dry. Let's have a look at that. So it's telling us, in fact, we don't need all of our variables. It's suggesting that the wind speed has a positive effect. In fact, we can, I think, We can show the ROC curve, for example. So this shows us our predictions of whether it will rain against whether it actually did rain. So that tells us basically how good our model is at predictions. We look at the ROC table. So it's basically telling us how many true positives, true negatives, false positives, and false negatives we get at different levels, okay? So that's basically an evaluation of how good our predictions are. We've got an AIC and a BIC. So it says R squared U, because we cannot apply R squared directly because it's a logistic outcome, meaning it's either 0 or 1, right? That's the only possible outcome. So R squared U is basically a rather simplistic comparison to R squared, which essentially tells us how good our model is, how much of the variability is explained by our model, and it's not great. So this is not a very good prediction model. And you'll see it's showing us the parameter estimates for the log odds of rain to dry. So this is telling us as the wind speed goes up, the chance of rain goes up. As the pressure goes down, the chance of rain goes up. So that's what we know. So most of you have probably never seen anybody who has a air pressure gauge in their home. But, in my grandparents' home, I still remember they had two very precious things in the entrance to their home. One was a grandfather clock. So that was a very large pendulum clock, accurate pendulum clock. So my grandfather could use this to make sure his watch was correct before he left home, because in those days, analog watches were not that accurate. And the other thing was a big air pressure meter, so he could check it before he went out in order to predict whether it might rain, so whether he needed to take his umbrella. Right, so we know that air pressure does indeed predict rainfall. And then the temperature also seems to be, if the temperature is higher within this data set, the chance of rainfall goes up a little bit. So this is a very small data set within a single month. So it's not surprising that the model isn't very good, right? We don't have a particularly good model here, but at least it enables us to fit models of this sort. So we can predict for binary outcomes the log odds. So log odds meaning the log ratio of the probability. So this is the log of the probability of rain compared to the log of the probability of dry. Okay, so this is helpful. If we do just a single variable, then JMP actually shows us a little graph. So let's just have a look. I'm going to repeat this just for fit y by x. So this time I'm going to do rain or not against wind speed. It doesn't work particularly well, but I'm just going to show you this for comparison. So you'll see in this one, it indeed does show that the wind speed is borderline significant after we remove temperature and pressure. But the nice thing is here, this little graph here shows us as the wind speed goes up, the probability of rain goes up relative to the probability of dry. So this is not a linear curve because it's linear on the log ratio scale, right? So this is plotting it, showing us the probability of dry and rained, not the log ratio of those two. That's why it is curved. So you can see that when the wind speed is 0, our model predicts about a 75% of dry. When the wind speed is 15, it predicts about a 80% chance of rain. Okay, so the model is not that great. We would probably need other variables in here to get good predictions or a much wider range of data. Okay, so this means that we can easily fit. So although the model here is quite different, again, this is an iterative estimation process. within JMP, we can easily switch between binary and non-binary data, and we can understand how this works. So for example, we could compare this to a model. Let's say, actually, let me just go back to, so let me do 2 fit y by x models. So we did rain or not against wind speed. We could compare this to the model where we try to predict the amount of precipitation against the wind speed. Okay, so this, you can see that the rained or not model is based on the amount of precipitation, but this model doesn't fit at all, right? So if we just try to fit wind speed against precipitation, this doesn't work well. Arguably, one of the reasons why is because this most certainly does not follow a normal distribution, because we have lots of zeros, and this is a very skewed distribution, right? So if we look at the distribution of precipitation, clearly fitting a linear model to this is not likely to work well, because we have lots of zeros. A quarter of our data at least is 0, and the median value is only 0.001, whereas the maximum is 2. So this is a very highly skewed distribution with lots of zeros. So it's not surprising we can't easily find a model. And in fact, what we're doing here in this logistic model is essentially just looking at the zeros versus the non-zeros, right? So it's not too surprising that this model here doesn't seem to work very well. In fact, if we looked at the residuals for this, we would see that this is not a good model, okay? So in a situation like this, then we can consider, so we could actually look also at amongst the days when it rained, how much rainfall there was, right? So that would be a different sort of model. And we might then look at the log of the amount of precipitation against different things. So in other words, there might be 2 different processes, whether it rains or not. And if it does rain, how much does it rain? So these are the sorts of things that we could look at in order to try and better understand what the process is. Okay, now what we're going to do now is something different. We haven't yet looked at the cloud cover. And indeed, we could have even looked at whether cloud cover predicts precipitation, right? So if we wanted to do that. Now, so at the moment, the sky cover in JMP is in there as a continuous variable, which it isn't. It is really an ordinal variable, right? It's quite clear because we can't get values less than 0. We can't get values greater than 10. And we don't know whether this is a linear scale or not. So we could, for example, have fit rained against sky cover. So we would expect this to be predictive, but you will see that it doesn't try and fit a linear model. It starts out by saying this is a contingency table, because ordinal means it has to look at each level of sky cover. So indeed, if we look at the significant test here, it says there is a strongly significant relationship between sky cover and rained or dry. So in fact, if you look at it here, if the sky cover is 7 or above, it always rained. If the sky cover is 3 or below, it never rained. But we have one situation here, sky cover 4, where it rained, and one sky cover 4 when it didn't rain. Right, so we know that this is not a perfect relationship, but clearly, if there is no sky cover at all, it cannot rain. That's the one thing we can say. But sky cover 10 doesn't necessarily mean that it rained. In this case, it did. Right, so if we change back to say that sky cover was continuous, then we can fit the model, but we know there should be some question about whether or not this is indeed an appropriate model because we know that sky cover is indeed ordinal, not continuous. But if we treated it as continuous, this does indeed say that so this R squared type measure now is relatively high. It's now about 75%, because as we saw, for most, with that one exception of sky cover of 4, in most of the other situations, it either rained or it didn't. And generally low sky cover, it didn't rain. High sky cover, it did. And it was this only one level of sky cover where it actually sometimes rained and sometimes didn't. Okay, so we can see, so this is a model for the log odds of rain dry, but again, it's a rather problematic because it's assuming that sky cover is linear when we know it's actually only ordinal scale. Now, but what I want to do now is to say, what about predicting sky cover? So what if we want to fit a model that predicts sky cover? Now, at the moment, this is continuous. That's not meaningful, as I said, but we can compare the two models, assuming it's continuous and assuming it's linear. So let's first of all try a linear model. And again, let's try temperature, pressure, and wind speed, okay? So if we put these three variables in fact, it says this is significant at about 3%. So what's the problem? The problem is that we expect that the residuals should be a bit problematic. So if we've got the residuals by predicted here, you can see that this is a rather, there looks to be some form of a pattern in the residual plot. And indeed, we know there is a problem because we can never get a sky cover less than 0 or never get a sky cover greater than 10. And we don't know that it's linear. But at least as a first approximation, if we only had linear models available, we might look at this and say, well, yes, it looks like as the wind speed goes up, the sky cover goes up. As the pressure goes down, the sky cover goes up. It's not clear that there's a temperature effect. We could remove the temperature effect, for example, and see, yeah, well, so it does still look like as the wind speed goes up, sky cover goes up, and as pressure goes down, sky cover goes up. But as I said, we know this model is problematic. So let's now change sky cover to being ordinal and see what happens if we try to fit a model now to sky cover. So we're again going to, well, let's do the directly comparison one with pressure and wind speed. If we put these two into our model, and again, you'll notice it's changed the personality to ordinal logistic. And we'll say something about what that means in a moment. So let's just run this model and compare it to the one where we did linear model. So if we compare these side by side, the conclusion is similar in the sense that it does indeed conclude that as the wind speed goes up, so this one, we need to be a little bit careful about how we interpret this. So this is actually in the reverse direction. So it's telling us as the pressure goes up, as the pressure goes up, we expect the sky cover to be less. And as the wind speed goes down, we expect the cover to be less. Right, so we have to be a little bit careful that it's actually written the other way around here. Now, you will notice, although we've said sky cover is ordinal, right, we still only got one coefficient for pressure and one for wind speed. Both these models, we conclude that wind speed is reasonably good evidence, and the air pressure is relatively weak evidence. So what's the difference between these two models? So in the ordinal model, you will see we've got all these different intercepts. We don't have a single intercept. We have multiple intercepts. That's because this ordinal logistic model assumes that as the pressure and wind speed change, the chance of going from one category to the next in sky cover is consistent. So look, it's basically assuming that the log ratios of successive levels of sky cover, that log ratio change depends on pressure and wind speed in a consistent way. So in other words, it assumes that pressure and wind speed affect my chance of going from 0 to 1, 1 to 2, 2 to 3, and all the way up from 9 to 10. However, in our model, it assumes that there are different intercepts for each of those log ratio models. So it's fitting the same coefficient on the right-hand side for pressure and wind speed, but on the left-hand side, we've got all these different log ratios that have different intercepts. So it assumes that ordinal means these intercepts are increasing. So from -133 up to -129. Right, so we've got essentially parallel models. So that's hard to explain here. So let's look at a simpler one. Let's do the fit y by x. So we're going to do sky cover just against wind speed so we can see. So this is showing us then how this works. So this is showing us all the intercepts. So it's showing the intercepts are increasing as we go across the categories. So it's telling us when the wind speed is high, we expect the sky cover to be high. When the wind speed is low, we expect the sky cover to be low. So you can see when the wind speed is 0, it's predicting roughly 30% chance of no sky cover at all. Another perhaps 10% chance of sky cover 1, and another 20% chance of a sky cover of 2. I got that right? Actually, no, sorry, we don't have any 1. So it's doing 0, 2, and 3. So it's basically saying there's about a 2/3 chance of a sky cover of 0, 2, or 3 when the wind speed is 0. And there's about a 60% chance of a sky cover of 10 when the wind speed is 15. So again, these curves are not parallel because we're showing them on the original scale, not the log scale. But on the log scale, these curves become parallel lines because we're assuming that the effect of wind speed is consistent as we move across the categories. Okay? So different intercepts, but a common effect from wind speed as we go across these different categories. So we can see actually our conclusion that wind speed is important is consistent between the linear model and the ordinal model, right? In fact, we even reached a conclusion that is more strongly significant in our ordinal model, probably because the data doesn't really follow a normal distribution. So in this one, for example, if we plot the quantiles, the quantiles don't look too bad. So on the face of it, it doesn't look too bad to assume that the sky cover follows residuals for a normal distribution, but we know that cannot be the case because it cannot be, sky cover cannot be less 0 or greater than 10, right? So we know by definition, this model is problematic. But as a first approximation, it turns out not to be too bad, right? In the sense that it reaches quite similar conclusions about the effect of pressure and wind speed as when we fit a proper ordinal logistic model. Okay. Yes. So the last one I want to look at today before we stop, I want to open Series G. So this one you cannot find in quite the same place. If you scroll down the list, you won't see Series G. That's because we need to look inside the folder called Time Series. So inside the Time Series folder, choose Series G. So I don't remember whether yours has log passengers in. Do you have log passengers in your version of the data file? Okay, so let's ignore log passengers to start with. This is time series data. It's quite a famous time series data. There's a very famous book by Box and Jenkins that was written, I think, about 40 years ago or something. I think it's the 1960s or 70s. I can't remember. 76. So this is approaching 50 years old, the book that this was first published in. So what we have here, just look at the first two columns to start with. This is data at 144 time points, where we have the number of passengers at those time points. So if we, for example, just did fit y by x and put passengers against time, you can see we get something that looks like this. So let me blow this up so that we can see it at a reasonable scale. So you can see that indeed the number of passengers increases with time, right? But it looks relatively random if we look at it like this, okay? So if you don't look too carefully at this, it looks like just generally, as time increases, the number of passengers increases. So if we fit a straight line to that, it explains a reasonable amount of the variability, right? The adjusted R squared is about 85%. So if we actually try to fit a linear model, if we try to fit passengers against time, sorry, I meant to do it within model. Let's do fit model because I want to use the diagnostic checks there. So if we flip passengers against time, that's not too bad. But if we look at the residual plot, that's rather more worrying. Why? First of all, you can see that the spread is not constant, right? As the prediction increases, the spread increases. So that clearly says to us that this is not, the variance is not constant. The other thing is you can also see there is some curvature here. So clearly it's not a purely linear model. Okay? And it does appear to be some sort of a pattern here. It's hard to explain what the pattern is. So the other thing we should check, remember I showed you before, one of our diagnostic checks was the Durbin-Watson test looking for autocorrelation. And this time it warns us the autocorrelation is very high. The autocorrelation is more than 0.7, which is highly significant. In other words, successive data points, their errors are correlated with a correlation of more than 0.7. So that means the R squared is about 50%. So if I try to predict the next data point passenger from the current data point, I can already predict it with about a 50% R squared. So it's a very strong effect. And this is the effect after removing the linear time effect. So after removing the linear time effect, there is still a strong autocorrelation. So this is clearly a data set which we should not be simply using normal linear models. So let's have a look. Let's ask JMP to help us. So we're going to say we want the specialized modeling time series. So if we fit passengers is our time series, and we're going to use time as our X time ID. If we do that, JMP gives us a plot that looks like this. So what is it telling us here? First of all, it's showing us that there is a strong pattern in our time series. So it's saying that there is a correlation pattern here on a time series basis. Now we have these two basic diagnostics. So this is telling us what the correlation is at different time lags. So in other words, if I want, so the first bit here, obviously lag 0, the correlation of the data with itself must be 1. This is saying at a time lag of 1, I have an autocorrelation of 0.95. So there's a very strong correlation of one data point with the next. And you can see this starts to decrease with time, but then it comes up to a peak again at a lag of 12, meaning time points 12 time units apart have a stronger correlation than any of the intermediate ones. Right? So that should tell us, that means there probably is a pattern here, a seasonal pattern. So this data is actually monthly data. So a strong pattern with a lag increase at 12 means there is almost certainly a yearly seasonal pattern in this data. And indeed, if you look at the other variables, you will see this variable called season is the month in the year. So that says we probably should account for that effect as well. Now, the right-hand side here is showing us what's called the partial autocorrelation function, which is essentially saying after accounting for the variables, the values in between, is there still a correlation? So obviously, there is nothing between 0 and 1. So we still have a very strong autocorrelation of adjacent time points, but it's saying if we look at lag 2 after accounting for lag 1, now we actually have a negative correlation. But again, the next big lag is at 13. So that's again telling us we need to account for the seasonal effect. So we can actually say to JMP, we want a seasonal effect. So this is what it calls seasonal ARIMA. So for now, what we want to do is a seasonal effect. So it's not immediately, so you can see here we have seasonal ARIMA observation per period 12. So it's already worked out for itself that it's probably a season of period 12. So we're not going to put the other terms in for now. We just do the simplest one, which says no autoregression, no differencing, no moving average, just observations per time period. So we can now, in our graph, show the seasonal effect. Right, so this says we can fit in here the seasonal effect. But I haven't yet put in the, I need to put in something more sophisticated in it. So we can, let me go back, sorry, let's try that again. Let's do the seasonal ARIMA. So the seasonal ARIMA here, so autoregressive and differencing is the two standard types of time series effects. That depends on whether we should be differencing the data or differencing the residuals of the data. So for now, we're going to assume we don't know what to try here. So we can tell it to try a range of models. So if we say we don't know which model to fit, we can try a set of ARIMA models within a range. So we want to try, let's say we're going to try 0 to 2 for the autoregression, 0 to 2 for differencing, 0 to 2 for moving average. So we end up with 27 different models. It's going to go off and fit all of these models and see how well they fit. So we can now look and see, it evaluates them in terms of the forecasts. So here we can see the graphs for all these different models and see how well these different models fit. So we want a report and a graph. So this one, for example, is the most complex one, 222, and a seasonal effect. So the question is, how well does this model work, which is the most sophisticated one of our set of models? So you can see this model fits remarkably well, that it generally is showing that it can cope with a pattern of variability in our data set. Okay, that's not too bad. So we can try all these different models, but let's go back. This is perhaps too sophisticated as a start point. Let's go back to our original data set. So we saw already that the passengers seem to be increasing with time. So what if we do this on a log passenger basis, and what if we count with the season? So first of all, let's account for the season. So what if the passengers, we put both the time and the season into here? So this is assuming a linear effect with time, but also a seasonal effect, which is nominal scale as a factor. So we fit this model. You will see that this model now is much better fit. We now have an adjusted R-squared of 95%. It tells us that both time and season are strongly significant, but now we can see in the residuals that we have even more clearly this quadratic effect, and with the variance increasing. Now, if the variance is increasing, that usually warns us that we should try a log transform. So let's keep this one on the left and repeat the same model, except we use log passengers as our dependent variable instead of passengers. So now our adjusted R-squared jumps up to 98%. Again, as far as the effect test is concerned, this is very strongly significant. And now you can see the residuals are a lot better in terms of the pattern, that the apparent quadratic term has gone away. The variability is reasonably consistent now. Again, if we do the check about the Durbin-Watson test, it tells us there is still a very strong autocorrelation. So removing the seasonality does not take away the autocorrelation, right? Even after we've accounted for the season. So still the errors in successive data points are highly correlated. So that means we do need something more sophisticated in our model, right? We do need seasonality, that's clear. We do need a linear time effect, that's clear, but we still need to account for the fact that the correlations, that the errors are correlated. So we can start with log passengers. We can put the time in here. So on a log passenger basis, it's even more clear now, but it doesn't take away the seasonality. We clearly have this seasonal pattern, right, consistently, and we also need to account for the correlation. So we would need to try fitting some of these other models, such as the seasonal ARIMA. As I said, this one assumes we know what the model is, so we're generally going to fit a set of ARIMA models. Sorry, let me just keep it simple. Make these all 0 to 1. So now we end up with just a relatively small number of models to compare. So we have these different models here. Let's look at the report of these different models. And we can look at the graph. So we know that the original ARIMA one, so this is basically saying nothing to see at all. This is just a constant. That's obviously a terrible model. This one here, you can see that doesn't work well at all, right? So neither of these two are useful. The third one you can see is much closer. This looks much closer to what's going on. The next one up, that also doesn't look too bad. So we can see that we at least need This is the absolute minimum of models that we need in here. We can look at these more carefully in order to try and work out which of these are useful. So this model here, we can look at the AIC to compare them. This was -66. That was the terrible model, right, with a constant. This one goes up to this goes to -202, -580, -589, back down to -368. So we can basically toss all the ones with very poor AIC. This one we said was -202. That still wasn't too good. -580, -589. Those are not too bad. This one is -368. This one is -414. Again, not nearly as good. -580 something, -580 something. So you can see we end up with these models. So there's the ones I have selected here. So this one is the 010 model, which is this one here. So you can see that one isn't bad at all. That has a Kaiki -580. This one is somewhat better, -589, the 011. So let's instead show the 011, which is this one. So you can see that one does indeed look very good. This one we said wasn't so good. -589, -586, that's not as good. -587, not as good. So we can see that from an AIC perspective, the one that we have graphed here is the best. This has 130 degrees of freedom. So meaning we started out with how many data points? 144. So this one has 12 lags. So this has 11 parameters for the, oh, I see, yeah, we can see the AIC on the left. Well, the AIC is on here. Ah, okay, I see, I just didn't move this far enough across. Yeah, thank you, yeah. So we can see clearly that most of these other models are not good enough. Of the ones I have looked at, this one, which is not the most sophisticated one, but it is close to the most sophisticated. So this one here is the most sophisticated, but the AIC is actually worse, right? So the degrees of freedom in our model, you'll see we've already got 12 seasonal lags, right? So that's 11 parameters plus 1 for the intercept is 12. And then we've got 2 for the moving average. So this is actually a relatively simple model once we've accounted for the trend, the intercept, and the seasonal pattern, right? So it's a relatively simple model, but this one accounts for the autocorrelation. Okay, so this is a clearly superior model to the simple linear regression model. So at the very least, with any data set that is time series, we should at least always check for autocorrelation. If there is autocorrelation of the residuals after fitting a linear model, that means we probably need to consider some form of a deeper time series model in this context of an ARIMA type model, meaning either that we need to difference the data itself. So a single differencing of the data corresponds to removing a linear trend. And then also differencing of the residuals relates to removing a correlation of the residual terms, okay? So it's relatively easy to consider these within this sort of framework, okay? So we have got to the end of the data sets inside JMP that I'm going to look at. So in our final session next week, you will need to have downloaded the additional data sets in the Google Drive folder. I will certainly look at the first 4 data sets, cherry tree, bacteria, iris, and Arctic. So the cherry tree is another one illustrating issues around finding a meaningful model. The bacteria is an example of looking at count data. So count data, our start point is usually a Poisson distribution, which we can fit within the generalized linear model. So that's again very easy in JMP. Iris is a multivariate data set, but where we're going to think about the concepts of size and shape for multivariate measurements of data. And then the Arctic one is an example of a compositional data set, meaning where our different components add up either to 1 or to 100%. So in other words, the variables must sum up to 1, and indeed they must all be non-negative. So that constraint affects our statistical analysis, because if the variables add up to 1, we cannot use correlations in the simple approach, because the constraint induces negative correlations on our variables. Okay, I have some other data sets in the set. The hormonal one, deviations, the KCS, time budgets, tripartite, US presidential election, the fossil. We can look at any one of these. You're saying they're not in the Google Drive? Let me just check. Where's my Google Drive folder? Oh, that's odd. What happened to my data sets? Okay, let me upload the data sets. So this is the additional data sets. Okay, so this is extras.zip. So you can download extras.zip before next week and unzip it, and then we will look at these JMP data sets in order to understand these additional issues. As I said, we will at least look at these first 4, cherry tree, bacteria, iris, and Arctic. If anybody would like me to look in particular at any of the other 7 data sets here, 20 to 26, you can tell me which ones you would like me to look at. Maybe some of these will be interesting to you, closer to your sorts of research problems. Then we can look at those. It's not a problem. And we'll see how time goes. So we'll just keep going. So at least we'll do these 4, and then whichever ones people have asked for from the remaining 7, or depending on what mood I'm in, I will pick some of these other ones to look at. Okay? So for those of you who haven't yet finalized your data set with me, please do so as soon as possible, because I would like you to get started on the data set. Now, we don't have a class next week. Next week is a public holiday, May the 1st. So our final class is on May the 8th. Now, for those of you who have installed the JMP trial, it will expire after 30 days. So it will expire perhaps before you want to do it. Now I'm going to check with JMP, see if I can get them to give me the extension license. If not, you may need to go and use the lab or purchase JMP or use something else, right? So in fact, we have done enough analysis by now that you should already be able to write the report. The things we're going to talk about next week, most of them go beyond what you need for the report, right? So you can even get started on your report now. You can submit your report as soon as you like. If I remember correctly in the book, I think I stated that did I state an approximate deadline in here? I'm not sure whether I said that. So generally, my expectation is that you will submit the report within 1 month of our final class. So the reason, yeah, I've said the deadline is 4 weeks after the final class. So that will be June the 8th.
right? Now, I encourage you to submit it sooner unless there is some reason why you cannot. So if, for example, you need to go off and do field work and you don't have time to do this, then I want you to tell me your proposed submission date, okay? Now, as I've mentioned, I retired from Hong Kong U at the end of June. I'm hoping that I will still be around on an honorary appointment, but obviously it's much better if I can finish off all the course assessments before I leave. In fact, I will be officially on leave as of the middle of May. In practice, all that means is I will be able to avoid university meetings as far as possible. I have many different things to finish off before my retirement date. So again, I encourage you to write the reports as soon as possible. I encourage you to submit them as soon as possible. Usually, I expect at least one round of revision to be necessary, where I give you some guidance on how to improve your report, right? So I can see it as an improvement process to give you some useful feedback in terms of what would be more appropriate diagnostics, or about your model choice, whether there are some additional models that you should be considering, okay? Again, this is a pass-fail assessment. So the reason for the feedback and revision is not because it will change your grade. In most cases, it's simply because I want to be quite confident that you indeed understand all the ideas in this course, and that you have developed the necessary skill set to do reasonable data analysis on simple data sets, okay? So please, if you have, so again, because we have a 2-week gap before the next class, please do not wait until the next class to sort out the data set. Please try and do it by Monday at the latest, so that in this next 2 weeks, you can get started on the analysis. And if you have any questions, you can send me questions before we have the final class, okay? So again, I know how things are. You all have many other things to do. So the sooner you submit the report, the better, because that means the sooner you submit it, the sooner I can give you feedback and you can do revisions and get this out of the way, okay? And as I said, I will try and see whether I can get a license extension, but if I can't, I don't, yeah, the grad school sent you an email. I've forgotten, I don't think they told me. They just included the email telling you how long you have access to the lab to. Here we go. Yeah, she included the email attachment. Yeah, so you have access till the end of May. So you have access to the laboratory in Run Short until May the 30th using your student card. So you can use that. As I said, also, you do not have to use JMP. If you want to use SPSS or R or anything else, I don't really mind. It's just that I consider JMP to be the most user-friendly and the easiest to use. It's not necessarily the most powerful tool, but at this stage, my key concern is that you have an easy-to-use tool, particularly as regards graphical diagnostics. Okay? Thank you all very much, and I'll see you all in 2 weeks' time.